Hello guys, welcome to today's class. Today we're looking at a very important topic, design of reinforced concrete. So we're making bias on Eurocode 2. We're making use of Eurocode 2 for our design. So right now we're going to start with the basics, deriving some basic expression, some basic parameters, and some basic equation which will now enable us to solve problems in designing concrete structures in our subsequent classes. So right now we have on the board we have a diagram of a rectangular section, singularly reinforced rectangular section in bending at equilibrium. Now, this is your section. You can see that this section, this rectangular section, you can see the line of the neutral axis with dotted lines. Now, below it is our tension zone. You can see these two notation we have here indicating the reinforcement provided, telling you that we have reinforcement only at the tension zone. Now, at the upper side is the compression zone. It's the compression zone. Now, the next one is your strain diagram. The strain diagram. You can see the ultimate strain, which is 0.0035. The ultimate. Now, the next one is your stress diagram or your stress block, indicating the ultimate stress of concrete, which is 0.567 FCK. You can see the X in denoting the neutral axis. You can see the D denoting the effective depth. You can see your X, which is equal to 0.8 X. You can see it's your FCC denotes the force in the concrete in the compression zone. Now, your FSD is the force in the tension zone. Now, you can see this denotation from here to here is your D. From here to here is your D, effective depth D. From here to here is your lever arm Z. Lever arm is equal to N over LAD lag. Then from here to here is your S over 2. Now, let's look at the whole thing proper. We know that concrete have high capacity of resisting compressive stresses. Concrete, a plain concrete, have high strength in resisting compressive stresses, but is not that strong in resisting tensile forces. It's weak in tension, but high and strong in compression. Now, with the introduction of a reinforced concrete, that's reinforcing the concrete will still have given us the ability of resisting different types of stresses, be it tensile or compression or even axial or anyone. So now let's start to derive some equation. At this very point, due to at bending, now, just try to look at this structure. Just assume that this structure, assume we have a section like this, and this section here is the section being loaded. Here is the span of the beam end. Assume that this is a beam section. Can be anything. Now this thing denotes the loading on it. Now at loading, the structure is under bending automatically. Now look at what happens in the layer. If you just go under bending in this very form, if you go under bending, here is the neutral axis. Now because there is a load, there are some loadings on this very section. It will induce a stress on this structure. This stress now will now give rise to the bending we have, and this bending we have will occur internally. You might not actually see it visible with your visible eyes, but it's happening there. Now, this neutral axis is going like this.